Hello everybody, welcome back. Today we're going to be looking at a problem that has to do with Bessel functions. So let's read the problem. From equation 15.4, show that the integral from 0 to infinity of the nth Bessel function equals integral from x to infinity of the nth plus 2 Bessel function. Then show that the integral from 0 to infinity of the Bessel function, the nth Bessel function equals 1 for n being an integer. Um, so that's a mouthful to write out and say in text. So I have it written again here in an easier way in blue. We need to show that the integral from 0 to infinity of, for example, j1 of x dx equals the same thing for j3 or any odd number uh, of j, and the same for 0, 2, or any even number. And then that last part is just that we need to show that it's all equal to 1. So, over here in black, I have stuff that's given, like this equation 15.4, or other things that we know about Bessel functions that we'll use in solving this problem. So, to start out with, I'm going to take this formula there and I'm going to rewrite it. I'm going to put uh, the p plus 1 Bessel function on one side of the equation and everything else on the other side. So it's going to be p minus 1 Bessel function minus 2 derivative of Bessel function. Um, yeah, and then so the next thing we're going to do is we're going to take the integral from 0 to infinity with respect to x. And since we know that these are equal from that formula, we can, anything we do on one side of the equation, we can do on the other side of the equation, including taking integrals and such. Um, so this is going to be the integral from 0 to infinity of the p plus 1 order Bessel function, and that's going to equal the integral from 0 to infinity of the p minus 1 order Bessel function. And then minus 2, and what's this last term going to be? The This is the derivative with respect to x. So the derivative with respect to x and the integral with respect to x are very good at canceling each other out. So this just ends up being just your normal p order Bessel function. But since we have limits of integration, we need to evaluate these at those limits. So, I'm going to just go ahead and rewrite this one more time. Because I want to write that last part in just a little bit different form. P plus 1 x dx equals 0 to infinity j, oops, it's a bad looking j, p minus 1 x dx. So this is going to be minus 2 times jp of infinity minus jp of 0. And, excuse me. In our little compilation of Bessel function facts here, we know that, or we see that for any order Bessel function, at least, so these all hold for integer p, which is what we're interested in this problem. So for any integer p, we know that the value at infinity, or as it goes to infinity, is going to be 0. So this term basically goes to 0. And then this term goes to 0, or is equal to 0, for everything that is not p equals 0. So for now, we'll just say that this is 0 for p does not equal 0. So what does this mean? This means that the integral from 0 to infinity of the j plus 1 Bessel function equals the integral from 0 to infinity of the p minus 1 Bessel function, with the stipulation that p does not equal 0. For p does not equal 0. So that actually takes care of all these situations. Because if p is equal to 1, then you have your 0 and your 2, which are these. And if it's equal to 2, then you have 1 and 3, which are those. So this takes care of all these situations. But I do want to go ahead and look at what happens when p equals to 0. And we'll see what happens. Okay, so I guess, so yeah, so this is, I'll go ahead and circle it. This is this first part of the problem right here. Just all in one instead of in two different lines there. So, what happens when p equals 0? We get the integral from 0 to infinity of p or j1 dx equals integral from 0 to infinity of j negative 1 x dx. And so what do we have here? This term is going to be 1, as we can see from this math fact up here. So it's going to be minus 2 times negative 1, or it's just going to be plus 2. So now we are going to use this fact here, that the negative order Bessel function is just equal to either the positive Bessel function or the negative Bessel function with the positive order. So so if p is equal to 1, then the negative first Bessel equation or Bessel formula is equal to negative the positive Bessel function, the first order Bessel function. So we're just going to go ahead and redo that here. I'll just go ahead and rewrite this. It's equal to negative this. And since this is like an equation that is true, we can substitute it in when we, wherever we want. The negative comes out of the integral, so that's fine. They are the same equation, so you can substitute them in wherever you want. So if we take this to the other side of the equation, then we have two integrals from 0 to infinity of the first order Bessel function. So if we take that and divide that by 2, what we have is that the integral from 0 to infinity of the first order Bessel function is equal to 1. Now, we already had this fact here, but by doing this, we just essentially found a new way to derive it. So that means that for 1, if we put, like I said, if we put p equals 2 in there, then we have 1. The integral is equal to the integral from 0 to infinity of the first order Bessel equation or Bessel function is equal to the third order integral and all that. But now that we know that the first order is 1, then we know that all the rest of them are equal to 1. So we can now say that all of these, you can't see that because it's behind my webcam, but all of these are equal to 1. That's a really bad way of saying it. But so we know that for all odd integers that the integral from 0 to infinity of that order Bessel function is equal to 1. And then all we have to do is use this math fact to say that all the other ones are equal to, all the even ones are equal to 1 also. There's not, well, I couldn't find an easy way to derive this, so you're just gonna have to live with the fact that it's something that's already proven. So that means for all the odd integers and all the even integers, that the integral from 0 to infinity of that order Bessel function is equal to 1. So that's what this asked us to find there. So we've proven it, and thank you so much for watching.